Today we're going to take a look at section 2.3, and we're going to talk about some set operations and properties for sets. So the first properties operation, or first set operation I want to talk about is an intersection. So a set intersection is a set that contains all elements that are in both of the desired sets. So you've heard the word intersection before. One of the places you've heard the word intersection is when you talk about the intersection of two streets. Okay, so MacArthur and Kickapoo out here are an intersection. And when you say something happens at the intersection, literally, of MacArthur and Kickapoo, you mean literally where they cross. So we're sort of close to the intersection of this building, but we're not in the intersection of those two streets, right? So if you actually wanted to talk about the intersection, you're actually physically talking about something that lies both on MacArthur and on Kickapoo. Are you with me? Okay. So there's some notation for that set. The intersection of two sets, if we have a set A and a set B, the intersection notation is an upside down U, or kind of looks like an N. And by definition, what this means, and we talked about this notation before, is this is the set of all X such that X is an element of A and X is an element of B. In other words, person is in the intersection of Kickapoo and MacArthur, it means they're both on the street Kickapoo and they're on the street MacArthur at the same time. Okay? It has to be in both items of description they're described. All right, so a union has the symbol that looks like a U. So to be in a union means you're in one set or the other set or both. Okay, one or the other or both. So the imagery that I like to think about when I talk about unions is what happens in a wedding ceremony. So at some point the preacher says something like this, and the two shall become one. And what does that mean? Well, it means that your parents are now my parents, and if you have children, they're now my children, and if you have debt, it's now my debt. You get it all, right? And legally, this is when things become really messy when people get divorced, is because then they got to separate that back out. It's all been mushed into one. It doesn't really work very well. So a union is when everything comes together and it creates one whole big mess. All right, you get everything from both groups of whatever you're talking about combined into one. And the notation for that is described as X such that X is an element of A or X is an element of B. And that or is the inclusive or. It means either or both. So it could be in the first set, it could be in the second set. It could be in both sets, and that'd be okay. Either or both. And then the relative complement is sometimes called the difference. So if you take contemporary math, it was called the difference when we teach it in that material. The relative complement, or the difference, is the set of all elements that are in the first mentioned set and not in the second one. All right, so when we're taking a look at this one, it looks like subtraction. And this is the set of all items, set of all X, such that X is in set A, it is in A, and it is not an element of B. Now, have we drawn Venn diagrams in here? Yeah. Let me show you some Venn diagrams for how this works as well. Because pictures are always good. All right, so if you have the intersection of two sets, we talked about how to draw oops, all right, hang on. Well, that'll work. All right, so we have two sets and they cross each other. So here's set A, here's set B, and here's the universal set out here. Then the intersection of this set is the part where they actually overlap. So it's this piece inside here. So let's do the same thing, the same picture, same starting picture for the next two. If we have I'm trying to draw it right over the words, so bear with me on that. If we have two circles that are overlapping over here, all right, so they're kind of big, but pretend like they're not. All right, so obviously if I color the overlap, that's the intersection, is the part that's in between. The union means I color both entire circles, and you get everything. Yours, mine, and ours, like the movie. Does anybody know that movie? Okay, same thing. Yours, mine, and ours. You get it all. Okay, so that's the union. And then to do the difference or the relative complement, here's set A, here's set B, and here's the universal set. So the description says it has to be in set A, but it cannot to be in set B. So that's just the outer sort of moon-shaped or the non-moon-shaped or whatever piece over here that we're talking about. So you're talking about taking everything in one piece and removing a portion of it that overlaps something else. Okay, everybody good? Okay, we're going to do an example. Consider Mary, single mom of one child, Mark, and Joe, single dad of two children, Beth and Jill. Mary and Mark get married. That's not right. I remember there was a typo last time. I can't remember what it was. Mary and Joe get married. So it would not be good for Mary to marry Mark. Let's let Mary marry Joe. Better. All right. Mary and Joe get married. Together they have two children, Ann and Andy. If M equals Mary's kids and J equals Joe's kids, find the following. So the first thing we're going to look at is M intersect J. Okay, so what does that mean? What would that mean physically in this description? Okay. They're both their children. Like combined, we had two children together, and that's Ann and Andy, right? So anytime you're doing these, you're putting curly braces. This is Ann and Andy. What about if we do the union? What's that going to mean? All the children. It's, you know, what we would do if we took a family picture, right? Everybody gets to be in it. All right, so we have who? We have Mark. Who else do we have? Jack, Jill, Ann, and Andy. Now what if I do M minus J? What does that mean in the context of the problem? Just Mary's kids. Did Joe die? I'll let Joe die. Actually, if Joe died, that wouldn't work very well in this description, because then Mary would still have 5 children. Maybe Joe's kids go somewhere else, the first 2 kids, but Mary would still have all of her children, or at least 3 children. So in this case, Joe's still alive. So M minus J means Mary's kids were married. It's the kids Mary brought into the marriage, right? Which was Mark. So we take Mary's kids, because Mary physically had the 3 children, the way it's described. She had Mark, Ann, and Andy. And then we remove from Mark, Ann, and Andy the kids that Joe had with her. That's Ann and Andy going down. We've got Mark left over. Does that make sense? Yeah, that's it. I should have closed it. Sorry. Yeah. There's Mark.
Could you also do like the J minus N?
Yes, you could. And then we'd have Jack and Jill, right? Mm-hmm. Good. Absolutely. And it would be a different set. So that's actually an interesting idea too, because when you're doing intersections and unions, the order doesn't matter. But if you're doing the difference, it would matter. So if we did, as you suggested, J minus M, we would not get Mark. Who would we get? Jack and Jill. Yeah. All right. So the next thing we're going to do is we're going to do some, well, actually, I just said that, we're going to do the properties of sets. So I mentioned this now, but we're going to write it down. So if you do the intersection of two sets, it doesn't matter the order that you do the intersection in. And when you change the order of something, that's called a commutative property. Commute, you know, like good, that you switch them. Commute. Okay. And then the same thing works for unions. And this works for all sets A and B. We can do this. It's not special, it's not a specific case. Any set will do this. Any sets will do this. There's also associativity. Associativity has to do with how you associate. So when you talk about who you associate with, right, sometimes you tell some of your friends, sometimes you just say they're kind of, I associate with them a little bit, like I don't really like them, don't know them well, whatever. Associate, people you talk to, okay? So it's kind of like who you're grouping yourself with. I mean, that's what it means when you talk about associate. Who do you associate with? Who do you not associate with? You're talking about who you group yourself with. And in mathematics, associative has that same connotation. It's about grouping. So if you're taking a look at this idea, and we'll do intersection first. If I do the intersection of A and B, and then I intersect it with set C, this is the same as intersecting B and C first, and intersecting with A on the outside afterwards. So the association, who we're grouping together, doesn't matter. You still get the exact same result. And the same is true for unions. So if I do A union B, and then do a union with C, I would get the same thing as doing the A union B after I did B union C. And again, this works for all sets. A, B, and C. Then you probably remember distribution. For whatever reason, of the three different properties that we have for real numbers, and that's what people do. Distribution is the one people remember. They remember commutative or associative, and then anything gets switched around in their mind. But everybody tends to remember distributive. So distributive has parentheses in it as well. But what it does is it talks about what happens outside the parentheses and how it transfers inside, right? So when you have multiplication on the outside, you've got like addition or subtraction inside. We talk about transferring that multiplication through the parentheses or something like this. And we have that same idea here. So if I have A and I have the intersection of B union C, so notice the symbols don't match, right? I've got an intersection in one place and I have a union in the other. Then the way that this distributes is this is A intersect B. So I'll intersect A and B together. So I'm distributing this A intersect here, and the A intersect is going to come over here to the C. What do you think might go between them? Union will go between them. And then this works for all sets A, B, and C. Okay, can I go to the next one?
I have a question.
Yeah.
Why do we need to know that it's for all sets?
It's just telling you that it's not a special case. It doesn't just work sometimes. Because there's lots of things that just work sometimes that don't work in general. And this is just telling you it's a general rule. So for me to say for all sets A, B, and C, it's telling you this always works. Yeah. All right, cardinal number formula tells you how to count things. You had no idea how to count before, now you will. All right, so if you have a union of two sets, You can count how many items are in that union by counting the number of items in set A, and then counting the number of items in set B, and then subtracting the number of items in the intersection. And I want to draw you a picture so you can see why that works, and I'll invade some of my space down here to do that. So, no, you're fine. Go ahead.
Intersection or an
This one, it's an intersection. They kind of look like the letter N, but yeah, it's an intersection. All right, so if I have set A here, set B, and this is my universal set, and I want to count the items in the 3 locations, the outside part of A, the overlapping part, and the outside part of B, okay? If I actually had numbers in each one of those locations, I can just count them up. That's fine, and that's not what you would be using this formula for, obviously. You can just count 3 numbers, and that's great. The problem is, what happens if you know instead how many items are in all of circle A? In other words, you don't know how many are out here and how many are in here. You just know everything in the whole picture. In fact, you know all of this piece right here. And then you also don't know exactly where the B elements go. You just know that there's some that are in the overlap and there's some in the outer part. So you know all of this piece right here. Well, if I count everything in red, you can almost think of it like an area. If I add up all the area that's in red, and I add up all the area that's in green, I've got a problem. That's what happens. I doubled up in the middle, didn't I? I counted what was in the middle and the overlap twice. So, what we can do is we can in fact do what I just said. We can count the items in A and count the items in B, but then we have to remove one of the countings that overcounted, one of the double counts. Okay? And by the same token, you can rewrite this formula in another way. You could actually move this piece, the intersection piece, over onto the left with addition, right? And you can move the union piece over onto the right with subtraction. And you have the same formula with the union and the intersection pieces switched around. That's kind of helpful. You want to know how many items are in the intersection, and instead, you know how many items are in the individual set and in the union, you can find the intersection pieces in the same formula. All right, Cartesian product is the last operation, if you will, that we're going to look at on sets. So this picture does not go with that, it goes up here. All right, so this is the set of all ordered pairs. So the first component comes from the first set, and the second component comes from the second set. So let me show you right now what this looks like. So product multiplication, right? The X symbol. So that's why we're using it, is because we've used the word product, and we use X when we first learn multiplication of product. So that's why we're using it here. And this is the set of all ordered pairs. All right, I'll write it this way, because I did before. Okay? These ordered pairs have property. The property is that the first piece, A, the little a, comes from set capital A. And the second number in the ordered pair comes from the second set, B. So we're going to do an example so you can see how it works. So let's say that we had a set A, which was the letters X and Y. And we have a set B, and they are the numbers 1, 2, 3. You've got 2 sets. These two don't happen to have anything in common. Even if they did, the process would be the same. Okay? So you've got 2 sets of stuff. Then if you're talking about the Cartesian product, A cross B, we're going to actually list them all out. Well, what we do is we take the first element in set A, which is X, and I write it as an ordered pair with the first item in set B, which is 1. So X1 is one of my ordered pairs. Take one item from the first set, one item from the second set, and make a pair of. But I could have taken point X in set A with what point in set B? 2, or element in set B, 2. Or I could have taken element X in set A with element 3 in set B. And that's the only different elements that I can group X with. X gets grouped with every element in group B. And I did that. But I also could have done something else. What could I have done? I could have done Y. And don't be misled to think that X goes first, Y goes second. X and Y are both in the first location because they're members of group A. Right? They're members of set A. So set A is where these items are coming from. It's the first set listed, so it's the first of the ordered pairs. So if I group, if I do my ordered pairs and I put Y, I can do Y with 1, or Y with 2, or Y with 3. And this would be the Cartesian product. So notice a few things. One thing you notice is that, again, this is a set. So it's inside the curly braces. Do you see those curly braces? Okay. But inside of the big curly braces, you have a bunch of parentheses items. Don't mix up your notation. I don't need parentheses on the big outside and then little curly braces on all those ordered pairs. That's inappropriate. Okay? Each of the items inside are an ordered pair in parentheses, just like in algebra, right? X, Y, ordered pairs in algebra. And then all of the set is in the curly braces on the outside. All right, so we're going to do a Venn diagram. And the Venn diagrams we're going to do are similar to the ones we had just done a moment ago, but I'm going to show you how to do some items with shading. Let's see how far we can go. All right, we're going to do this slide and one more for today, okay? All right, so the first thing we're going to do is we're going to look at a grouping of 2 sets. And we talked about this notation last time, that bar on top. What does that bar on top mean? Remember? Remember that? It's complement. So from contemporary math, remember the prime notation, complement, this is complement. What is the complement of set? What does that mean? The opposite, everything not in it, right? So if I talk about a complement in a picture form, I'm talking about everything outside of circle A. Okay? All right, so I have 2 elements, or sorry, not elements, 2 sets right here, A and B. So when I draw my Venn diagram, I'm going to draw the same picture that you've seen me draw on the previous slides, where I have the rectangle, always there, with the circles on the inside. And the 2 circles overlapping. Okay? And we're going to call this set A, set B, and set U. Everybody get so far? Now, we can probably reason this out without the method I'm going to show you next. Okay? So let me just say that first. I realize there are other ways of doing what I'm about to show you. That said, this is the one I want you to learn. And the reason is because it will generalize very well to the next slide. Okay? So we're going to work on it in a simpler case so that we can generalize it to the next slide. Kind of like when you're problem solving, right? We did very concrete, easy examples so that we can generalize it to a bigger case. That's the idea. Here's what you're going to do first. You're going to label each one of these regions with a number. They don't have to be the same numbers I have, but if you do different numbers, your numbers aren't going to match my picture, so you might want to use these. Okay. What we're going to do next is we're going to come over here and we're going to put the set down, A complement, and we're going to look at our picture, and we're going to list the numbers that are in A complement. That is, we're going to list the numbers that are not inside of circle A. And what numbers are not inside of circle A? 3, 4. So we're going to list them. This is 3 and 4. So A complement, everything outside of circle A includes region 3 and region 4. Okay. We're going to do the same thing with B complement. I look at my picture. I want to list every number that is not inside of circle B, which is 1 and 4. And then I'm going to join these 2 pictures, these 2 descriptions rather, with the union symbol. What does union mean? Both of them have? Be real careful. What do you mean by both? Okay, that's intersection. So So the one they have in common that both of them have would be a description for intersection. What's the description for union? All of it. So when we're doing a union, we get everything. Remember, it's the wedding ceremony thing, right? Yours, mine, and ours. So we get everything. So when I'm doing the union here, I'm going to list every number that I've already listed, which would include numbers 1, 3, and 4. Now, the directions said to shade, so please do not do what some of my students have done before and forget the last part, which was the actual part of the directions. Go back to the picture and shade those regions. So this says I'm supposed to shade region 1. So region 1 needs to be shaded in. Please don't shade it in so dark that I can't read that that was your number 1. Okay? You can use another color if you want to, that's another option. It also says I'm supposed to shade region 3, so that's this piece out here. And I'm supposed to shade region 4, which is the outer rectangular box. We have this picture. Make sense? I know there's other ways to do this. I'm not trying to convince you that there's not, but this works really well in it. Okay, we're going to do another one that's 2 sets though before we get there. No, wait, we're not. We're going to do it right away, 3 sets. All right, we're going to do A intersects B union C. So how many sets do I have? I have 3. So I need to draw a rectangle. And inside of my rectangle, I need to have how many circles? 3. All right, so here's set A, here's set B, here's set C, and this is the universal set U. Obviously, I need more than 4 numbers, right? Because I got lots of places where things overlap, don't I? Yeah. So I'll show you where I put my numbers. Again, you can do whatever you want as long as your picture matches the numbers you pick at the end. It's fine. I usually start here with A, and I go across the top, 1, 2, 3. I go across the middle, 4, 5, 6. I put 7 down here in circle C, and then 8 on the outside. And all these numbers are is they're giving me a place to call that. They're giving me a name for that spot. So I use numbers. All right, so we're going to come back over here. And just like in algebra, one of your order of operations, remember order of operations from algebra? PEMDAS, PEMDAS, you may remember an acronym, something like, please excuse my dearest Sally, or something like that. Do you remember what the P stood for? Parentheses. And just like parentheses are the first place you start in algebra, parentheses are also the first place you start in set theory. So we're going to work inside the parentheses before we move outside. So inside the parentheses, I have circle A, or set A, which has my circle over here in my diagram. And I'm going to list all the numbers in circle A. And I'm going to get what? 1, 2, 4, and 5. Good. And then I'm going to list set B. What numbers are in circle B? 2, 3, 5, and 6. Okay, so now I've got the individual sets that are in the parentheses. What do I do with them next? I do the intersection, the operation that combines them. So this is A intersect B. Okay, so this is the one that you guys mentioned earlier. This is the both idea. In order to be an intersection, it must be in both of the lists above. What numbers are in both lists? 2 and 5, and those are the only ones, right? So the intersection here is 2, 5. And now I've done everything inside the parentheses. So once that's done, I can move outside the parentheses, and then I've got set C that it's talking about. So I'll do C next. All right, what numbers are in circle C? 4, 5, 6, and 7. Okay, so now I know everything inside the parentheses, which numbers those are. I know the numbers for C, and then I'm going to do the operation that's between them, which is what operation? It's a union on this one, right? This U right here. So now I want to take A intersect B and do a union with C. So when I do a union, what happens? I write them all down, don't I? Not everything from the entire problem, but everything from this step right here. The step before where I had the two things that I was joining with the union. So I list what? And notice I don't need to list 5 twice. I mean, I suppose I could if I really wanted to. It doesn't really help me. It's only going to get shaded once. So I don't really list I don't list repeats. Now I need to go back to my picture and shade those regions. So I've got to shade region 2, region 4, region 5, region 6, and region 7. And that's my shading for that. We're going to stop right there. We'll do section 3 so we can remind ourselves how this is all working next time. It'll be a good way to get back into it. So we'll pause here.